Okay, guys. So myself Amit from TVZ Electronics. In this video, we will actually be looking how to make an ESC, electronic speed controller. So let's see. First of all, let us see ESCs. So electronic speed controller is basically a thing that takes uh, input from your battery or any other power source and gives output to your motor uh, the way you want to drive it. Okay, so ESC is actually not only limited to the standard servo signals that uh, like many people in robotics use. ESC can ESC can also be made like using a button. Like if you press a button, it will rotate one way. If you press another button, it will rotate another way with speed control and all. So basically, anything that drives a motor is called electronic speed controller. Okay, so as you can see, this is one ESC. This a brushed ESC for brushed motor. This is again bidirectional ESC. Bidirectional ESC is basically ESC that drives a motor in both forward and reverse direction. And we will see how to make a bidirectional ESC in this video. And this is again another ESC which is for brushless motor. Brushless are basically three-phase DC motors and they need commutation to rotate the motor. So these are a totally different concept from brushed motors. We will cover brushed motor today, and I will basically start from scratch and show you how every component works in an ESC. So this project will be basically open source, and every schematic I will put it on GitHub and share the link. So please join TVZ community. We are just getting started. There are many more projects to come. So first of all, let's see what is an ESC. Okay, like very basics. ESC is a physical unit. Two power wires come plus and minus. There are two outputs that go to motor, and there is a signal wire. Uh, this is a typical ESC used for robotics. We will focus on robotics right now. So this signal takes PWM input from your transmitter, from your receiver, the radio controller, and it translates your input, your joystick input, into the speed of the motor. And, so now, as we know how ESC works, now I will show you uh, the components that ESC uses. All right. So the components are basically the building blocks of ESC, different ESC. So actually I wanted to show you something. This is an ESC that I have designed myself, the hardware, firmware and all. This is basically a 4S ESC. It can deliver up to 30 amps continuous without any heat. Like on, if you stall the motor, it will get slightly warm, but 30 amps it can deliver continuous. It has standard RC receiver, two power wires, and two outputs. And you can see this is the, yes, it is still in prototyping stage. I have not yet tested on different kinds of motors. So yeah, we will be seeing how to make this kind of ESC. Uh, Now let's see what is a MOSFET. Alright, so MOSFET is basically, you can consider a tap. There is input stream of water, there is output stream of water, and there is this rotation, the valve of the tap. So when you control the rotation of the valve, then you can control the output of the water, right? So similarly, MOSFETs do the same thing. There is this drain, there is source, and there is gate. There are three pins: drain, source, and gate. So basically, what happens? Uh, uh, a power source is connected to drain, and a voltage is applied at gate, and then voltage the higher the voltage, the more current will flow through a MOSFET. So MOSFET is actually a voltage control device. This is to be noted. Uh, and the transistor, the normal BJT transistor, are current control device. Like the IGBT is also a current control device. So we will use MOSFET. Typically, MOSFETs are used due to its like high efficiency. So this is basically MOSFET, and this is the first component of an ESC, and another one is gate driver. Okay, gate driver. So gate driver is basically a small IC. The IC may be of different form factors, different footprints. So gate driver is basically an IC that takes input from the microcontroller that you will be using to control the logic of your ESC, and microcontroller will provide signals to the gate driver, and gate driver will turn on and off the gates of MOSFET. Because see, many microcontrollers work on 3.3 volt and 5 volt, and it cannot provide MOSFETs enough power to drive the gates. Okay, so they are logic level MOSFETs, but still it can't provide enough current to fully turn on the MOSFET. So in my ESC, if you can see, this is the microcontroller. I'm using Atmega 328P, the same as Arduino Uno and Nano. And these are the gate drivers. And here below the heatsink, there are MOSFETs. So this is the gate driver, and this is the third component, the microcontroller. Microcontroller basically what it does, it takes input from the coming the RC controller, RC receiver, the standard servo signal, and then it translates the signal into suitable values to turn to say the basically to say gate driver how fast and which MOSFETs to turn on and off. Okay, so this is about the components. Now, now we know what components are used. So basically, now we will look at component selection. Okay, so first of all, MOSFETs. So in ESC, general rule of thumb, we always use N-channel MOSFET due to its low switching losses. Okay, we can use P channel plus N channel combination also, but P channel, although it is like easier to turn on the MOSFET, but P channel has very high resistance, RDS on drain to source resistance. I will show you in the datasheet. So we use N channel to reduce the switching losses. So let us see N channel MOSFET. And also one thing, in designing an ESC or any other power circuits, as general rule of thumb, the current you want and the MOSFET rating on paper, the rating should be way more, like 2 to 3 times minimum or 5 times more than the actual current that you will be using, because those are the on paper factors, and those are, I think, tested in lab control environments, but in real life we don't get those numbers. So one popular is IRF Z44, and this is a very good MOSFET. very popular MOSFET, and those the clones are very cheap actually. So we'll just take a look at data sheet. It's from Infineon. So yes, you can see in the first page only, right? The first three factors are VDSS. This is voltage drain to source. Okay, this is the symbol of MOSFET. Okay, this represents the internal body diode of the MOSFET. Uh, Through this only it can block the reverse flow of current. And you see this is VDSS. It means voltage from drain to source. How much it can block. So till 55 volts you can apply. Although you should never go above like 45 volts for a safer margin, but 55 volts is the max limit, physical limit of the MOSFET. So after 55 volts, the body diode will get shorted and it will start reverse conduction. And this is RDS on. Okay, this is drain to source, like drain to source resistance. Resistance it is 17.5 milliohms. So the lower the resistance, the higher current can flow without heating up. Okay, without using much energy, so it will produce less heat. It is 17.5 million. One, I think it was there. Infinity IR 3205S. Yeah, this one is a very good MOSFET with lower RDS on. There are many MOSFETs with much lower RDS on. You can search on LCSC. You will get tons of MOSFETs. You can see here the RDS on is only 8 milliohms, and this is ID. Okay, the drain current, continuous drain current, it is rated 110 amps, but it is never 110 amps. Don't even expect it to be 110 amps. Here you can see the absolute maximum ratings. Okay, these are absolute maximum ratings as I told on paper. This is current drain, this factor, this current drain. Let me zoom in. Yes. The drain current at junction temperature at 25 degrees Celsius. Okay, the PN junction of the MOSFET at 25 degrees Celsius, and if you apply 10 volts between gate and source, then it will be 110 amps. But this is not practically feasible. Okay, even if the junction temperature is reaches 100 degrees Celsius, uh, then also you can see it can provide 80 amps. Okay, so these are on paper rating, but you can expect up to like 30 40 amps uh, in real life, that too with proper cooling, either be active or passive cooling. And these are pulse drain current, like instantaneous current that people say the ESCs that are rated for, like 2 second 3 second instantaneous currents. These are all the factors. There are many factors, we will not look everything. One is power dissipation. Okay, this is, it can dissipate 200 watts. It is not electrical power, it is basically most probably the thermal power that it can dissipate, like how much heat it can handle. So these are 200 watts. But yeah, these are basically the core parameters that we see while choosing MOSFET. There are obviously many parameters like this one. Yeah, one is total gate charge. Okay, gate charge is necessary because the lower the gate charge, the fast you can switch on the MOSFET. Because what happens is that when you apply voltage to gate, okay, there is a parasitic capacitance between gate and source. So you first need to charge up the parasitic capacitance, then only you can continue to turn on the MOSFET. So this is the total gate charge, okay, the gate to source. So there are several breakdowns like gate to source charge, gate to drain, the Miller charge. When you will probe with oscilloscope, you will see when charging the gate, there is a like it charges up, then there is like plateau region. That is called Miller's plateau. We actually need to like lower the Miller's plateau, like charge efficiently, and this is the, like, you need to basically focus on main the total gate charge. It is 146 nanocoulombs, and it is tested at a drain current at 62 amps and voltage VDS at 44 volts and turning on at 10 volts. So if we reduce the drain current, then basically the total gate charge will also come down slightly, but not so much. There are huge calculations involved which I will not show, obviously. So we understood the MOSFET selection, so we'll use this MOSFET only, IRF3205. So let's fire up our EDA software. I'll use easy EDA for this one. And it's quite slow. I'll use new project. So first, let's search for IRF3205. Yes, assembly. Yeah, and while using the components, we'll also need to take care of the footprint. Okay. So uh, before using the component, if you are using for prototyping and production and all, you need to first search for the availability of the component. Okay, it is like on Flyrobo, it is 26 rupees. Obviously, it is not original; it is clone, because you won't get such high power MOSFET at 26 rupees, but still you can use for prototyping and low power applications. So the footprint is SOT 263. Okay, so see, SOT 260, TO 260 is the same. You see, it is JSM, I don't know, it is JSM semi. We'll use this. I will place 4 MOSFETs, and I will explain why we use 4 MOSFETs. Let's mirror it, change directions. Okay. So first of all, now we need to understand a brushed motor, a bidirectional controller brushed motor works in the circuit. It is called an H bridge. Okay, the the current flows from one terminal to other terminal, and the other terminal to the first terminal in the opposite direction. Hence, it is called H bridge. So I'll show you why it is called H bridge. So first of all, the high side of the MOSFET, the side that is directly connected to the positive power, that is known as high side. These are common terms. The high side of the MOSFETs are basically connected to the battery. Okay, I will I'll just name the net as VBAT. Is it recording? Yes. And the the source of the A side, like the source of the left side, is connected to the drain of the left side. Okay, this right here. Similarly, this side also. The source of both sides are connected to drain of the low sides, and the source of the low sides are connected directly to the ground. And now you will get, now this is one motor output, and this is another motor output. So our basic H bridge, basic motor driver circuitry is almost complete. Okay, now I'll show you what happens. It is very interesting. You see, when you want to rotate the motor in clockwise direction. Okay, so what you do, you turn this and these MOSFETs on together. Okay, so basically the current will flow from VBAT to this MOSFET like this. It will go through motor winding, it will rotate the motor and come back from this MOSFET to the ground. And if you want to rotate in counterclockwise or other direction, you can turn on these MOSFETs. The voltage will come from here to the MOSFET winding and then through here. Okay, and you may ask why it is not going above, like from here the connection is there, so it can go from here also. You see the body diode I told you about. This body diode helps in that. This body diode helps the reverse flow of current. So if uh, the voltage you apply is above the VDS, it will short circuit and fry the MOSFETs. So now we always to rotate the motor, we always switch in like diagonal pair. Okay, we never switch on this MOSFET, because if you will switch this Q1 and Q2 together, the VWAT and ground will be shorted. So we all know the electrons find shortest route to travel. So the current will flow from VBAT to Q1 directly Q2 and ground. So this will fry up this to MOSFET. Okay, so this is the basic working of the MOSFETs. Now, what we need to do, uh, we need some way to turn on these MOSFETs, all right? Because uh, we know now how MOSFET works. We cannot directly switch the MOSFET through any microcontroller, because the GPIO pins of a microcontroller does not have enough current to drive the MOSFETs. Okay, so we need gate driver IC. Gate driver. We'll search for the gate driver. There are many gate driver ICs, like tons of gate driver ICs. See if I can see this. I'll show you the gate driver IC of this ESC. My internet is a bit slow. Yeah, you can see here SL2103, IR2104S, UCC. These are all gate driver ICs. Okay, so this is 34 rupees, this is 69 rupees. Let's use a cheaper one. Let's see first. Let's see the data sheet. Okay, SL2103, SL2103 data sheet. Let's see what it says. Not getting here. It's from Silco, if I'm not wrong. Let me search on LCSC then. So LCSC is basically a great site to search for parts and its data sheets. Like even if the parts are not available in India, you can still search for the like the most efficient parts that you can use. Yes, so we can see it's manufactured by Silcor, and this is the one that I'm looking for. the data sheet now. Yes, this is the half bridge driver IC. So it means that it can drive only half side of the bridge. So Q1 and Q2 only it can drive. So we'll need two ICs, two half bridge driver IC per full bridge. So you can see V offset is 600 volt max. So it can easily handle uh, the 12 volt that will be used to drive the gate. And the current plus minus is source and sink current 130 milliamps and 270 milliamps. I guess it's enough to drive such small power small MOSFETs, and the V out is 10 to 20 volts, the output that it will provide to the gate, and the turn off time is typically 680 nanoseconds to 150 nanoseconds. Okay, one more important factor is in gate driver ICs. Uh, Sorry, in H bridge, we cannot instantly switch the MOSFETs. Okay, for example, if this MOSFET and this MOSFET was on, and if I instantly switch on this MOSFET and close this, between this time, like even if it is there a nanosecond delay, the Q1 and Q2, these MOSFETs can get shorted and it will blast in the sense it will get fried. So we typically need a dead time. Uh, Dead time is basically time between switching of the another pair of MOSFETs. Okay, so when Q1 and Q4 are on, if I want to change the direction, Q3 and Q2 will be on, right? So we will first turn off Q1 and Q4, wait for few like milliseconds or nanoseconds, then turn on Q2 and Q3 so the MOSFETs do not get shorted. Okay, so some gate drivers have basically inbuilt dead time and some we can configure. Oh, sorry, this is not dead time. This is turn on and turn off time for the MOSFETs. This is the dead time, 520 nanoseconds. And here features we can see. This is 3.3 volt, 5 volt, and 15 volt logic compatible. So 3.3 volt can work with STM32s, and 5 volt with AVR boards, Arduino, Uno, Nano. 15 volt logic I don't know who uses. Cross conduction prevention logic, and match propagation delay for both channels, so one one does not lag in switching like the pair, and it is SOP8 package. So here you see the typical application circuit is given like this is the MOSFET, this is the gate resistor, this is connected to high out, this is low out, this is voltage supply, this is VCC. Yeah, sorry, this is not voltage supply. This is the VS that goes to the motor terminal, the first terminal. So I'll show you the wiring diagram. Let us use SL2103 SOP8 from SIP. I don't know why it's taking so much time. So one is here and one was already placed. Okay. So first let's do one side connection, and we always use a gate resistor. Okay, I'm showing you why we use gate resistor. Let's open. uh, I don't have oscilloscope right now, so I'll just show you the plot of the graph that we get without using gate resistor. Okay, I tried that and I burnt many of the MOSFETs I didn't know previously. So like this is a typical graph. When you turn on the MOSFET without a gate resistor, uh, the we remember we talked about the gate charge, total gate charge, the Miller's plateau. What happens is that the voltage rises at the gate, and then this part rises and then it starts swinging. Okay, like this the voltage will rise instantly, and since it is rising first, it will start to swing and then settle. So we need to avoid this swing part. This is known as gate ringing. It may fluctuate the MOSFET, like it will be on off, and this will basically damage the MOSFET. So this part is known as gate ringing. So to prevent the gate ringing, we typically use a very small resistance, like from 10 ohms to 50 ohms. Between that, we need to test for different MOSFETs. So uh, here we need the ideal graph is like this. Okay, yes, like it should be as smooth as possible, as smooth. But when you zoom in the oscilloscope, there is always some ringing, but there it won't be perfectly smooth, but there is some ringing. But we basically need to minimize the ringing effect. So that is why gate resistor is used, because if we use a higher value resistance, then the switching will be low, I mean slow, and then there will be more switching losses. And if we use lower power resistance, or sorry, lower resistance, or if we don't use resistance, then there will be this gate ringing which I told you damages the MOSFET. So it is like finding a sweet spot between the 10 ohms to 50 ohms resistance. These are typical values. So we will use one resistance, and these are different packages. Let's use 1206 size. Let's put resistance here on the gate. Yeah. So now the first gate will be connected to the high out of the gate driver. Okay, because this is high side, and the high side output will be connected to the high side MOSFET, and the low side output will be connected to the low side MOSFET. And the Vs is the voltage that is applied at the motor terminal. Okay, between the between the drain of the first between the drain of the high side MOSFET and the source, sorry, between the source of the high side MOSFET of the first half and the drain of the high side MOSFET of the first half. Vs is connected here, and now we will apply a voltage to the gate driver to drive the gates. Okay, we don't use the VBAT at the gate driver because it is like too high. We can't use like 45 volts, 50 volts, 25 volts to drive the MOSFETs. Okay, so let me make a net level. Let us say this is 12 volts, and this is high in and this is low in. Okay, so these pins are basically, this is active low. Okay, so these two pins, these are microcontroller pins. Okay, the microcontroller will control it. The common is always connected to the ground, the com, and this is VB. Okay, this is uh, for bootstrap capacitor, the voltage for bootstrap. Now let me explain just in a brief what is bootstrap capacitor and why is it needed. So bootstrap capacitor is basically a small capacitor value ranging from like 0.1 microfarads to 1 microfarads, or like 2.2 microfarads, like it's not very much but not also like very low. So this will be connected from VB to VS. I think yes. Here see the bootstrap capacitor is connected from VS to VB, and there is one diode which is used to charge the capacitor. So this is we typically use like a Schottky diode. So I will, since we are using assembly, I will basically use one SS34 diode, typical like very commonly available part. You can check the footprint. I'm just using it. We'll correct the orientation and then connect the diode. Yes. Um, Now the bootstrap diode is also connected, and one filtering capacitor is present between VCC and ground. Don't mind the messy circuit, I'm just explaining it. So this is zero point 0.1 microfarads is good value. Typical value we don't use much, and this usually range from like 0.1 microfarad to 2.2 microfarads. That's all. And we mostly use ceramic capacitors, okay, MLCC, multi-layer ceramic capacitors with X5R or X7R ratings. You can search all this on where you will find. And these are microcontroller pins, okay. So I'll not do the wiring here. It is same, the exact same thing you need to connect here. And now coming to the microcontroller part, okay. Microcontroller, anything you can use. I will just explain the logic here. All right. So let's see, if you want to, let's say we want to make a bidirectional ESC, okay. So bidirectional, what is it? Bidirectional means both direction, CW and CCW, okay. So we use in robotics we use a standard servo signal which is usually a PWM signal. So we'll say PWM signal, and it ranges from 1000 microseconds to 2000 microseconds, and the center is 1500 microseconds. This is the basic thing that we are given with. Now what we need to do is uh, we need to translate the input of the joystick, the on the radio controller, the joystick. We need to translate the input to the actual gate drive signals. So the microcontroller, what it does, it takes the PWM signal from the receiver, it translates the signal, and then it sends to the gate driver IC, and gate driver IC then takes the logic signals, and then it drives the MOSFETs accordingly. Okay. So what we do now, like basic structure of code I am giving you, we will first define uh, the pins of gate driver. Okay, the gate driver pins are defined in microcontroller, and after that we will first read the signal of receiver. Okay, we read the signal, and after that uh, map the signal to PWM value. Okay, because we cannot directly use the raw values 1000 to 2000 microseconds, because the digital signal is the PWM value is 0 to 255 range in the Arduino microcontroller, the Atmega 3283. We are focusing on that. We can use other microcontrollers also, but the logic will be same. So we are mapping the signal to PWM value. This is actually for the custom firmware that I had written. So this is the logic for that. Okay, I'm not giving away the uh, giving away my own firmware. I'm just providing you the logic, the block. So map the signal to the PWM value and feed the value to the gate drivers. Okay, so if you want to rotate clockwise, what we will do? We will do uh, we can write digital high, say high in one, uh, let's say at value 255, and if we write here high, this first high MOSFET we will write, then second the second half of the bridge, the low side MOSFET, we will have to write the low in. Okay, the uh, low out value that was there, we will have to write that low because it is active low. Okay, if it is high, the low side MOSFET will be off, but since it is low, it will be when we will put low value, then only it will start conducting because it was active low. So we need to keep this in mind also. So this is basically how we can make a ESC. This was the basic, uh, the raw schematic, like not the actual schematic, but the raw one. I will make one schematic and the PCB files, and I will upload in the GitHub, and the link will be shared in TVZ community. You can join. I'll put the link in the video description. Yeah, so that was all, and let me show you my ESC. Okay, yes, you see, this is the PCB of my ESC. I have not shown anyone. This is my ESC. This is the signal connection. This is the ground positive. And yes, one thing that I forgot to mention, that we'll need to use voltage regulators to regulate the voltage. Like we need to provide 12 volt to gate drivers, right? So I'm using a 12 volt regulator right here. We need to provide 5 volt to Arduino at Mega 328P, and the receiver. So I'm using this 5 volt regulator. You can see these are the MOSFETs, and these are the flyback diodes. We can just ignore the flyback diodes. I had just put there for extra protection. This one is bootstrap capacitor. This is SL2103. This one is diode, the bootstrap diode. These are just some filtering capacitors. You will need a lot of passive components. Okay, and this is power indication LEDs. This is a failsafe indication LED. And yes, I'll tell you how failsafe also works. All right. So in this, you can see here they are saying there is reverse option, which obviously we are using in this ESC. I have shown you the logic how reverse works. There is signal loss failsafe, and there is regenerative braking. I don't know if Rust ESC needs regenerative braking, how they are implementing, or if they are just writing for marketing purposes. And isolated heatsink plate, yeah, heatsink we will need. So I'll basically show you now how failsafe works. Okay, it is very interesting thing. You see, sorry, let me show you paint. So this is, suppose this is graph, okay. When you provide input uh, from your joystick to the receiver, what happens is that it takes a pulse value from 1000 microsecond to 2000 microsecond, okay. Like the more you give, the more it will be the width of the pulse, okay. So what happens, this there is a range of time, okay. For example, uh, like there is a frequency, how fast it is. For example, just for example, if it is 50 hertz, okay, or let's say instead of frequency we use time, okay. For example, each pulse is received in 2 milliseconds, or like this. Just for example, I'm saying it is not typical, uh, not standard, I'm just saying it. So uh, even if it is, even if the throttle is at zero, we are still receiving 1500 microseconds value every 2 milliseconds, okay. So that is how the microcontroller is knowing that the position is 1500 microseconds, and we need to stop the motor, we don't need to move it. So each 2 milliseconds, like 2 millisecond, 2 millisecond, 2 millisecond, 2 millisecond, it is receiving a valid signal, okay. It is receiving a valid signal. But what happens if I disconnect the signal, okay. So after this, the 2 millisecond, 2 millisecond, 2 millisecond, the fourth 2 milli till 4 times 2 milliseconds periods, it is receiving a valid signal. And if I disconnect it, it the fifth time it does not receive, okay. So the microcontroller will enter into a check mode, okay. Like it will start checking if it receives valid signal. So for example, if I say for 100 milliseconds, for 100 milliseconds, if it does not receive, for 50 milliseconds, if it does not receive the valid signal, we will just turn off all the MOSFETs, okay. Every MOSFET will be signaled to go into the low state. So what happens then is that each MOSFET goes into their low state, and the all the conduction stops. So uh, you know, the motor stops rotating. This is how failsafe works, the signal loss failsafe. There are many different failsafe, like battery voltage failsafe, like under voltage failsafe, and transmission loss failsafe. Like if the transmitter gets disconnected, then there is also another approach to failsafe. It is quite complex. We usually use signal loss failsafe because in during drive the transmitter rarely turns up. The There is high probability that the receiver will get disconnected many times. So signal loss failsafe is more than enough for robotics brushed ESC. And one more thing I forgot to tell is that when we feed the value to gate drivers, okay, we usually when we read uh, when we feed the value to gate drivers, some gate drivers have built-in dead time. Like in this we saw 520 nanoseconds, and some don't have the built-in dead time, so we can adjust the dead time internally. Some have like programmable dead times, or some have we can adjust using resistors and resistor divider and all. So this one has fixed dead time 520 nanoseconds. It is more than enough. We don't need to do anything. And one more thing, uh, before reading the signal of receiver, okay, we need to add a dead band of say uh, 20 to 50 milliseconds. Okay, this is the dead band. Dead band means that you see in robotics, okay, the transmitter, the the joystick that we use, it is not actually 100% precise, okay. There is always some fluctuation, like tiny vibrations it is present. So the it can so the like, transmitter can give off random values, okay, garbage values. So we need to prevent it. So we add a dead band of 20 to 50 milliseconds. Like if we push like little bit tiny till 20 milliseconds, after that it will start reading the values. So the vibration that is occurring, it won't be happening. Like it won't take the values into account. So it will be like good. It is a good approach to prevent uh, like randomness in the drive. So this was basically everything. How you can see. And you see in my PCB, I'm using a lot of wires. These are connecting from top layer to bottom layer. Okay. So and instead of wires, you can see I'm using copper areas, direct solid copper areas. This is necessary because you are handling high power, not like one. So uh, using copper areas is always recommended. You can see I'm not using any wire traces here, right? I'm directly connecting here. This positive is directly connecting from here to the MOSFET's drain. You can see direct copper area. So yeah, these are all the key factors that we need to keep in mind while designing an ESC. And I will definitely put up a PCB, uh, testing a prototype PCB and schematic on the GitHub. I will share the link very soon, and you guys can start making your own PCBs if you want. It now just the programming depends upon you because I will not be sharing my own firmware. Uh, it is a proprietary thing, and it took me like many years to do trial and error. Okay, so you see this ESC that I was showing. This is a result of around 4 to 5 years of constant, uh, what to say, constant trial and error. Okay, like around 70 to 80,000 rupees was wasted in prototyping the components and all. And one more, I will showing you one piece. Just a second. This you see, this is one of the prototype boards that we were using. This one was one gate driver. This was another gate driver. We were using with two different set of MOSFETs and two different set of gate drivers. This was like the fourth iteration of the test PCB that we are using. This came out at the ninth iteration. This thing. So and I have many more types of prototype PCBs. Like we have tested around 16 times. We have made different circuits. We have uh, we did not order all 16 circuits. We have made around 16 schematics. Then we found some flaw. Then we again redesigned. And around around ninth iteration, eighth or ninth, this came on this piece. This works flawlessly now. I just need to test in real life, and then I'll put it up for sale if anybody is interested. It has signal loss failsafe. It has 30 amps continuous current at 4S, and I'm also making it half the size. This is basically around 3 centimeter by 6 centimeter. I'm making 3 centimeter by 3 centimeter size. Yeah, so this was it. This is all about the ESC. So yes, let's end it right here.